Swayam Prabha. Digital India. Educated India.
Welcome back everyone, and in this module we'll be continuing our discussion on the general oscillatory, small amplitude oscillatory motion, and we continue with our examples. So our continuing topic of discussion is general small oscillations. And we find, let us recall with an example of the double pendulum. The problem says find the general equation, the general solution of small oscillations for the double pendulum. So we want to write the general solution, right? If we recall, so most of the work is already done in previous modules. We have already found the normal frequencies, the normal amplitudes, and of course the normal forms of the solutions. If we recall, the normal modes were theta given by epsilon times cos of, so the slow mode was 2 by 3 nt minus, so the first solution, this is the slow mode solution, so we put a 1 to distinguish it from the second solution. So theta and phi was 2 epsilon 1 cos of square root 2 by 3 nt minus gamma 1, and the second solution was theta given by epsilon 2 cos square root 2n minus gamma 2, and phi is minus 2 epsilon 2 cos of square root 2 nt minus gamma 2. Okay, so then we would like to write the general form of the solution. The general solution is theta is epsilon 1 cos of square root 2 by 3 nt minus gamma 1 plus epsilon 2. So we add up these two solutions to find the most general form, cos of square root 2 n t minus gamma 2 plus, and the second part of this, the second generalized coordinates, the general solution can be written as 2 epsilon 1 cos of square root 2 by 3 nt minus gamma 1 plus, minus 2 epsilon 2 cos of square root 2 nt minus gamma 2. Okay, so that's what we have, and notice that typically this general motion is a combination of two motions, one with a slow mode, one with a fast mode. So we expect that if we want to find, visually it seems that this solution is periodic, but to find the period, we can be absolutely sure the solution is periodic if it turns out that the ratio of the two frequencies is a rational number. Otherwise, the solution is not periodic and any trajectory will never be closed. So what we have is, if we find in these two cases, if we find the ratio of the two frequencies, omega 2 by omega 1 here, the ratio is to square root 2 by square root 2 by 3, we see that this is square root 3. So this is an irrational number, which means that we cannot have a common period of this solution. So this is a non-periodic system. right? Simply having a linear combination of two trigonometric functions cannot guarantee a periodic solution unless and until the ratio of the frequencies they are a rational number, and this result has been discussed in detail in one of my previous SwayamPrabha course on nonlinear dynamics. So listeners are requested to see that course. Thank you. And then now I'm going to discuss another. See, we have seen the motion of the equation of small oscillatory motion, where we have written the V matrix and the T matrix. But typically these matrices are not written in a very convenient form. Why? Because for an n by n system, the matrices will have n entries, and fortunately it turns out that we can simplify this setup by changing our coordinate system in such a way that these matrices, they become purely diagonal. So we will now introduce the notion of the so-called normal coordinates. Normal coordinates. So normal coordinates. So the idea is, let me write the definition. A set of generalized coordinates in terms of T and V matrices such that T and V matrices having diagonal form, right, is called the normal coordinates. Okay, so to begin with, our coordinate system in which we had described these matrices for the approximate form of potential and kinetic energy were Q, which were the generalized coordinates. So Q was our original choice of generalized coordinates. For V and T matrices. So in that case, we have T approximate given by Q dot T Q, and V approximate given by Q dot transpose TQ and QTQ, right? And we saw that if we change the coordinates somehow, so we would like to consider the change in the Q matrix to N matrix, such that what we have is that Q is P times eta, right? So we have to find this coordinate of matrix of coordinate transformation P, such that Q transforms to a new coordinate eta, such that the matrices of V and T becomes diagonal, right? So or eta is this matrix P inverse Q. Okay, so then I can write my T approximate as P eta dot transpose. So that is my T approximate times T times P eta dot. So then what we have is that this is also equal to eta dot transpose times P T P transpose, right? So we just we do all the processing. We see that this is also equal to this, and then we see that so T being a symmetric matrix, we expect that So this, so we would like, so this has to be eventually equal to this form, eta dot, well, eta dot transpose t eta dot. So in such a way that now T, this new matrix T is diagonal. This is going to be diagonal. Okay. So so this is what our requirement is, and in that case eta will be our normal coordinates. So this question now is that what should we choose this matrix P such that T becomes diagonal. So this question is about the choice of P, such that T and V are diagonal. The choice of P such that these matrices are diagonal, and we would like that. So how to do that? So it turns out the answer to this problem is we choose our normal coordinates eigenvectors, AJs. We choose them as columns, and those are the columns of, we choose those vectors as the columns of the matrix P, and that P will work. So the answer lies is, again, the answer to this question comes from the standard theory in linear algebra, right? So we choose the columns of P as the amplitude eigenvectors. We choose the columns of P as the amplitude eigenvectors AJ. Right? So we choose that. Okay, so then what we have is, let me rewrite. My matrix P is A1, A2, A3, AN. So this is my matrix P, and in this case my P transpose TP will be nothing but AJ TAK. This is because we have chosen the columns of P to be the eigenvectors AJs. So this is the same operation we saw in the previous module, and we see that this is also equal to delta JK. That is what we had seen earlier. Or in other words, in matrix notation, this is equal to an identity matrix. So only when J is equal to K, then delta JK is 1, which means only the diagonal entries are 1. Otherwise, off diagonal entries are 0, or we have got the identity matrix. So so that's it. Now similarly, if we see what happens to the V matrix. The V matrix is P transpose V P. The V matrix is such that we have 0 omega j square and j not equal to k and j equal to k. We saw that if we do the same operation, again this is from the Rayleigh minimum principle, right? So from the Rayleigh minimum principle, if we multiply, do this vector matrix multiplication operation, we used to get omega squares on the diagonal, otherwise omega square on the off diagonal, 0 on the off diagonal. So which means that from here we see that P transpose VP is going to be identity, and otherwise this is going to be omega square. PVP transpose is going to be omega square, right? And we assume that in this case, if we divide by these frequencies omega square, then then what we can see is that, well, so this is what we have. Well, this is the final result in terms of for the potential energy. Okay, so what we have is that eta is P inverse Q. So eta is our new coordinates P inverse Q, and or otherwise from this choice, from this particular equation that we had written for kinetic energy, the kinetic energy matrix, this is also equal to P transpose TQ, right? P transpose TQ, and this is our normal coordinates, right? So eta is this, and these are our normal coordinates. Okay, normal. So this is what we have. Okay, so we have found the normal coordinates, and now we would like to write down. So let us revisit our small amplitude oscillatory equation of motion and see what they look like in normal coordinates. So in normal coordinates, that is in eta, we see that the small amplitude oscillatory equation will have the form which is eta double dot plus omega square eta is 0. Again, how did we get this form? If we go back to our equation, small amplitude oscillatory equation, which was written in T and V form, and we pre-multiply by P transpose and post-multiply by P that equation, and use the distributive property of the matrices, we will reduce it into this particular equation using the transformation for the matrix T and V. Using the transformation for matrix T and V. Right? And what we have now is that let us look at this case, this particular result with respect to one of our previously solved examples. So the example is again the case of the double pendulum. So if we revisit our double pendulum equation, we see that our T matrix is half mb square 4 1 1 1, and our A1 is 1 comma 2, and our A2 is 1 comma minus 2. Right? This was our kinetic energy matrix, and now let us now drop this constant. So I'm going to drop this constant because this is just a constant. We can eventually divide this constant in our matrix equation throughout. So that is not a problem. So now if we want to find what is eta 1 and eta 2, the normal coordinates, this will be nothing but A1 transpose TQ, right? A1 transpose TQ, and eta 2 is nothing but A2 transpose TQ. A1 transpose TQ and A2 transpose TQ. So we see that this is also 1 comma 2, the matrix 4 1 1 1, and again if we write Q is nothing but our coordinate theta and phi. We see that our coordinate eta 1 comes out to be after all this multiplication comes out to be 6 theta plus 3 phi. Similarly, we do the same exercise and we see that eta 2 is 2 theta minus phi. 2 theta minus phi, and we have got this result. So if we were to write this entire result in matrix form, then eta 1 and eta 2 have the form which is given by 2 comma 1 and 2 comma minus 1 theta comma phi, right? So so what we have is that eta 1 and eta 2 are in this form. So if we can divide eta 1 throughout by 3, we will get 2 comma 1, and in the other one 2. So we see that these are this 2 comma 1 and 2 comma minus 1, these are exactly the eigenvectors that we had found for the double pendulum problem. So these are constituting the matrix P, the columns of the matrix P transpose, right? So we want, so this is nothing but P transpose, right? Okay, so so that should be the idea should now be clear how to use the normal coordinates. So now let us shift our focus on the 3D rigid body dynamics, and so what we have is we are going to revisit concepts like vector angular velocity, and rigid body kinematics. So this is in 3D, right? And the key concepts are we want to study are the vector angular velocity, and the rigid body in the general 3D motion, the general motion. Okay, and so the major idea that we will see as we go through the examples is that in the most general form, the rigid body motion is the vector sum of both the translational motion as well as the rotational motion of the body. So so now let us look at both these types of motions one by one. So the first thing that I would like to point out is that of the rotational motion about a fixed axis. Rotational motion about a fixed axis. So the definition, so what we have is, let us revisit the definition of rigid body again. So rigid body, right? So a body B is a rigid body. A body B is a rigid body if the distribution between any pair of its particles, the distribution of about between any pair of its particles remains constant. Okay, that is, if we have two particles Pi and Pj, these are particles of the bodies in the body B, particles of B, right? Then with position vector, let's say Ri and Rj, with Ri of T and Rj of T, then these position vectors are they are fixed relative to each other, or Ri minus Rj, they are fixed, right? So these are constant. Okay, so then we can similarly define what is angular velocity. So we saw that again for a rigid body, so of B. So we typically denote angular velocity with the vector omega, and the omega has a direction which is normal to the, or along the axis of rotation, or normal to the plane of rotation, right? So where this n is the unit vector which is normal to or which is parallel to the rotation axis, parallel to the rotation axis. So the question remains that we want to the idea is, what about this plus minus? It turns out we always use the right hand rule of finding the direction of rotation, and if the motion is anti-clockwise, then our right hand points upwards and the motion is said to be having a positive sign, so we put a positive sign. Otherwise we put a negative sign for an for a clockwise rotation. So that is the notion here. So let us now look at let us start with a simple example and highlight this idea. So the example says a rigid body is rotating with angular speed. It's rotating with an angular speed of 7 radians per second, right? And it is given about a fixed axis, right? So let us say a rigid body is rotating with an angular speed of 7 radians about a fixed axis through the points A, which is 2, 3, -1, and B, which is -4, 0, 1. And the rotation is left-handed. In the sense relative to AB. And we want to find the angular velocity of the body. B. So we are given 2 points. We can write down the position vector of the points. So the position vectors of these points in IJK form, in the vector formulation, position vectors of A is, let's say, small a given by 2i plus 3j minus k, right? And B is -4i plus k, and what we see is now so our axis is fixed through these points AB. So if we were to find the position vector AB, then AB will be B minus A, and this is -6i minus 3j plus 2k. Okay, so that is our position. Now we know that the axis of rotation is parallel to this vector AB. So our axis of rotation n hat is going to be a unit vector which is parallel to AB, and this is going to be -6, -3, 2 divided by the norm of this thing, and we get that this is -6i minus 3j plus 2k by 7, right? And then which on the other so what we get is finally is that omega is the angular velocity is going to be the amplitude of the angular velocity is given to be 7 radians, and the rotation is left-handed. That is given in the problem. So the magnitude is -7 because the rotation is left-handed, and then n is this quantity. So we can cancel. So n is this vector by 7, and what we get is that omega is 6i plus 3j minus 2k. So this is a simple problem here, and of course this is in radians per second. Okay. So then if we were to find well, so what we have is if we were to to describe the angular velocity or to describe the rotation of a body, we need to fix the origin of the frame, the reference frame. And suppose the origin of the reference frame is fixed on one of the particles on the body, then our formula for the angular velocity changes slightly, right? So we need to rewrite our with respect to our new origin. So what we have is that suppose our rigid body has an origin O, and we have a fixed particle with position vector B, right? So fixed particle B with position vector B, and we see that what we have is let B this particle this position B be a fixed point. Let B this point be a fixed point on the rigid body. On the rigid body, then what we have is that R is the position vector. R is the position vector of the particle relative to the origin. Of the particle B relative to the origin O, and then in that case we see that the velocity of the particle P is given by V is equal to omega cross BP, right? So P being the position vector of the particle, right? So which means that P is the position vector of the particle, which means that our translational velocity of this object with respect to this new reference point is going to be omega cross R minus B. Okay, so then what we have is let us quickly revisit this example. I think I'm all out of time for this module, but in the next module we will revisit one example related to this angular velocity, and then we will look at the general rigid body kinematics.